Right. So good morning, everyone, and welcome everyone for this morning session. Our first speaker this morning is Professor Gurmeet Bakshi from Punjab University, and she will speak on revisiting Brauer-Witt theorem from computational perspective. So, Gurmeet, please begin your presentation.
Thank you, Professor Varma, for the introduction. And first of all, I'm thankful to the organizers for inviting me to speak at this conference. And very, very happy birthday to Professor Kulkarni. I have great regards for him. I first met him in 2008 when he came to Chandigarh for ATM school. He stayed here for a month, and later on he came to several ATM schools in Chandigarh. And what we realized that we have a similar interest in group theory. So I really enjoyed talking to him about groups, particularly the simple components of group algebras. And off and on, we met at several occasions, several places, and we resulted in a collaboration. And I really learned a lot from him, that the way he thinks, he just thinks at the grassroots level. And that had a lot of impact on my further research. In fact, from our joint publication, several works came later on, which I have with my students, and which is a byproduct of that publication. And so I'm very thankful to him for the influence on my research. So I'll be speaking on revisiting Brauer-Witt theorem from computational perspective. So throughout this talk, all groups are finite. Q is the field of rationals. QG is the group algebra of G over Q, and IRG, by IRG I always mean complex irreducible characters of G. Okay. Now, for any irreducible character of complex irreducible character of G, if you look at this expression E chi, it's a group ring element. It's an element of the group ring CG. And this is a primitive central idempotent of CG. It's a well-known result. It's in fact one of the basic result in character theory, that this is a primitive central idempotent in CG. And now, if you sum over those E chi's, for those chi's which are Galois conjugate, so you look at EQ chi is the sigma in the Galois group of Q chi over Q.
Hello?
Yes. Yes.
Gurmeet, I think we lost your voice.
Okay. Okay.
Just one moment.
All right.
Yeah, just Gurmeet, just 2 minutes.
Yeah, sure.
Yeah, put it on full volume. We will switch off ours. Okay, you may start again.
Yeah, I start from the beginning. Yeah. All right. So G is a finite group. Is this okay now?
Yes.
All right. So throughout this talk, all groups are finite. Q is the field of rationals. QG is the group algebra of G over Q. And IRG is the set of complex irreducible characters of G, standard notations. Now, for any complex irreducible character chi of G, if you look at this E chi, this is a primitive central idempotent of the complex group algebra CG. It's a well-known result in character theory, is one of the first results. And then if you sum over E chi's for those chi's which are Galois conjugate, then you get a primitive central idempotent of QG. So this is my notation. This I will be using the standard notation EQ chi for this, which is a primitive central idempotent of CG, of QG. Now you generate ideal with this EQ chi. That's a simple component of the rational group algebra QG. QG is a semi-simple algebra by Meshke's theorem. And this is a simple component of this. It's a finite dimensional. This is a finite dimensional central simple F algebra. And the center of this algebra is F, which is known to be Q chi. To Q, you adjoin all the correct values. So what is the structure of this algebra? What Wedderburn proved that this finite dimensional central simple algebra is isomorphic to matrix rings over a division algebra. So let's look at these finite dimensional division algebras with center F. So this is a well-known result that its dimension over its center, the dimension of this division algebra over its center is a square. This is a well-known result. And if you look at the maximum, and this D has a maximal separable subfield. There is a maximal separable subfield of D. Of course, it contains F. And the dimension is the square of this dimension. So this sits precisely in the middle of D and F. So this dimension is the square of this dimension. Now, this K is just separable, finite and separable extension of F. You just enlarge this K to a field L so that this becomes a now finite normal separable extension, which is a Galois extension of K. And then this also gets enlarged to matrices over D, and then one can show that this L sits inside these matrices over D. Now this algebra, this is a central simple algebra, MMD. This has the property that it has a maximal subfield, which is a Galois extension of it. Now, because of this fact that this is a Galois extension of F, by using Noether's column theorem, one can prove that this matrix algebra over D, so-called B, which I denoted by B, is a cross product algebra of L with the Galois group of L over F. It is this B is the cross product algebra of L with the Galois group of this extension. So from D, we have shifted our attention to MMD, and this has become a cross product algebra. And here I will just give standard notion of Brauer equivalence. That two central simple algebras are called Brauer equivalent if some matrix algebra over A is isomorphic to some matrix algebra over B. So D is Brauer equivalent to matrices over D, which I have denoted with B. So this simple algebra in which we were interested, QG EQ chi, is Brauer equivalent to D, and D is Brauer equivalent to B. And now B is a cyclotomic algebra. B is a this. So our given central simple algebra in which we were interested, the simple component becomes a cross product algebra. What Brauer and Witt proved, that this cross product algebra is Brauer equivalent to a cyclotomic algebra. Cyclotomic algebra is a cross product algebra where the extension is where this extension is a cyclotomic extension. So you can replace L with a cyclotomic extension E of F, and these two are Brauer equivalent. And this is Brauer-Witt theorem. And now in the proof of Brauer-Witt theorem, this precise description of the cyclotomic algebra is not available. So the proof relies on the existence for each prime P of a P elementary subgroup of G. P elementary subgroup meaning that there is a subgroup which has a cyclic normal subgroup co-prime to P, and the factor group with that cyclic normal subgroup is of prime power. So the proof relies on the existence of such elementary subgroups of G such that the P part of the simple component is same as the P part of the simple component corresponding to this P elementary subgroup. So, but finding these P elementary subgroups, there is no such algorithm or method how to determine these P elementary subgroups so that one can see the structure of that cyclotomic algebra and in turn result in the structure of the simple component QG EQ chi. So this theorem of Brauer-Witt was improved by Altiano in 2007, in which instead of using P elementary subgroups, they use strongly monomial characters. And they said that the class of strongly monomial characters is large as compared to P elementary subgroups. P elementary subgroups are strongly monomial in fact. And therefore, one has a better description of the Schur index and the simple component. But again, the problem lies in finding those strongly monomial subgroups of the group G, for which they heavily depend upon the use of gap. And gap, of course, cannot handle computations beyond certain limit. It has computational limitations. And this is the next objective, that how can we describe the precise structure of the cyclotomic algebra without theoretically, without the help of gap. For general arbitrary given class of groups, what will be the structure of the simple component? And this work of Altiano was implemented in the gap package Viderga. But again, our concern now is that how can we build a general theory from that? So the reason, I have told you the reason of Altiano's work, that because there is no method to determine P elementary subgroups, and so they shifted to strongly monomial characters. And the advantage is that, again, I told you that the class of P elementary subgroups is smaller and the class of strongly monomial characters is wider, so the problem becomes easy. So this is my recent ongoing work with Jyoti, in which I will give you just what I'm using strongly monomial characters and generalized strongly monomial group. I will soon introduce you to this. What we have proved is that for generalized strongly monomial character of G, this simple component is isomorphic to matrix algebra over this cyclotomic algebra, very precisely given what is this E, what is this F, and what is this action sigma, what is the twisting tau, all from the subgroup structure of the group. So now let me introduce what are these generalized strongly monomial characters and how big is this class of generalized strongly monomial characters. So I will have to go back to strongly monomial characters or generalized strongly monomial characters. What is a monomial character? Monomial character is the one which is induced from linear character of a subgroup of G. Now, what is that subgroup? What is the property of that subgroup H, so that if I take a linear character on H and I induce it to G, it is irreducible. And this is the work of Shoda, that he said that these two are precisely the necessary and the sufficient conditions, so that if you take a linear character on H with kernel K, then lambda induced to G will be an irreducible character of G. So if you want to look at monomial characters of G, all you need is a pair H comma K of subgroups of G with these two properties, and then you take a linear character on H with kernel K, induce it to G. It's a monomial character. So this is the work of Shoda, and in his honor, these pairs, any pair of subgroups with these two conditions is called a Shoda pair. So monomial characters are in 1-1 correspondence with Shoda pairs. As I told, if you have a monomial character, you have a Shoda pair. If you have a Shoda pair, you have a monomial character. Now, what's a strong Shoda pair and what is the need? See, given a monomial character, the aim is to determine the simple component QG, EQ, lambda induced to G. The aim is to give this the structure of the simple component. Now, if you add this restriction, these two restrictions on the pair H comma K, that H is normal in the normalizer of K in G, and the distinct G conjugates of EQ lambda. EQ lambda is a primitive central idempotent of QH. Distinct G conjugates of EQ lambda are orthogonal. This looks strange, but these are natural conditions, as I will tell you. They come from Clifford theory. If you add these two conditions, then it is possible to give the structure of this simple component QG EQ lambda induced to G. If lambda is a linear character on H with kernel K, H comma K is a Shoda pair with these two conditions, then one can describe this algebra as a matrix algebra over a cyclotomic algebra, and that was the work of Oliveira, Del Rio, and Simon for strongly monomial characters. These are strong Shoda pairs, and strongly monomial characters means monomial characters which are realized by strong Shoda pairs. Now, I will describe the class of So again, strongly monomial groups, known examples are abelian by super soluble groups, but not more examples which are not abelian by super solubles. So this is the biggest class of groups which is known to be strongly monomial is abelian by super soluble group. And groups where irreducible characters are induced from linear characters of normal subgroups, they are also strongly monomial groups. Now, we improved this notion of strong Shoda pair. We said that this is a joint work with Gurleen, which was published in 2019. We said that if you have a Shoda pair, then instead of having that one property that H is normal in the normalizer of K in G, and the distinct G conjugates orthogonal, we said go with a chain, that there is a chain of subgroups of G such that at every step, the similar thing is happening. HI is normal in the centralizer of the next one, and the distinct G HI plus 1 conjugates are mutually orthogonal. Okay. So having done this, now the question is it really meaningful? I mean, what is the advantage of doing this generalization? The advantage is huge. I will come on that. So this is my notion of generalized strongly monomial groups where all irreducible characters are realized by generalized strong Shoda pairs. Now look at the class of generalized strong Shoda pairs. This class of generalized strong Shoda pairs is very, very vast, which we saw in a recent paper, again with Gurleen, Journal of Pure and this is just published now. We have seen that all monomial groups of order P to the A, Q to the B are generalized strongly monomial. Super monomial groups are generalized strongly monomial, odd order. Not written order here. Nilpotent by super soluble groups of odd order are generalized strongly monomial. Monomial groups with Silo towers are generalized strongly monomial, and many more. In fact, what Isaac conjecture is that every monomial group of odd order is super monomial. This class of super monomial groups is conjectured to be such a big class. And then there is a lot of work of Isaacs did on monomiality questions, normal subgroups of monomial groups are monomial or not, and so on. So the various monomial groups appeared in those classes in the work of Isaacs and Dade, Lois, Lokaki. And we proved that all the known examples of monomial groups are generalized strongly monomial. So we are not able to find so far any example of a monomial group which is not generalized strongly monomial. So in fact, we improved Dade's embedding theorem, that Dade proved that every finite soluble group can be embedded inside a monomial group. What we proved that it can be embedded inside a generalized strongly monomial group. It was the same work with Gurleen. Now, having done that, So the class of generalized strongly monomial groups we understand is big, but our interest is the simple component. So we generalize this class so that we are able to give the simple component. Now coming to that, what is the description of is chi? When chi is a generalized strongly monomial character. All right. Now look at a generalized strongly monomial character chi. As I said, chi is generalized strongly monomial when chi is lambda induced to G, where lambda is a linear character on H with kernel K. This is what I said. And the pair H comma K is of course a Shoda pair, and it has the property that there is a chain of subgroups of G such that those conditions, two conditions hold, that HI is normal in the centralizer and distinct HI plus 1 conjugates are mutually orthogonal. So such a chain we call as a strong inductive chain. Such a chain of subgroups we call as a strong inductive chain of this character chi. So if I have this generalized strongly monomial character chi, then I have this chain with me. I call this is not unique, but this is one chain I am taking. And then this is a notation. Ci is the centralizer in HI plus 1 of EQ lambda induced to HI. This is the centralizer. And what we have is that HI is normal in Ci. This is in the conditions of generalized strong Shoda pair. And the index of Ci in HI plus 1 I'm taking as Ki. In this work with Gurleen, we saw that Ci mod HI is normal in Ci, that is our requirement. So Ci mod HI makes sense. It acts on this simple component. This is a simple component of the group algebra QHI. This acts on this simple component by conjugation. Because of the fact that HI is normal in Ci, if I take an element of Ci, then it will act on this by conjugation, because it will centralize this. It will centralize this. This is my assumption that HI is normal in, because I'm taking something in the centralizer, and therefore this will act on this algebra by conjugation. And so you have an action, and you also have a natural twisting. I'm not going to the details because then it will become very technical. And one can show that this algebra is matrix algebra over the previous algebra. So basically what you are doing, you have QH0 EQ lambda, and then you have QH1 EQ lambda induced to H1. So successively you are trying to tell the answer. Sorry, I am sorry. I'm going to go back. Yeah, this is EQ lambda induced to H2 and so on. So first I have this. This is easy. This is just Perlis-Walker theorem. The structure of this algebra is just Q zeta, where zeta is nth root of unity, n is the index of K in H. This is easy. Now, then what Oliveira Del Rio Simon proved, that this is a cyclotomic algebra over this. So the structure of this is known from the structure of this. What we said, that the structure of this is known is a cyclotomic algebra over this. The next one is a cyclotomic algebra over this one, and so on. So this was a generalization of that work of Oliveira, that each time the next algebra is a cross product algebra over the previous one. And this gives rise to this theorem, appeared in the same paper, where we introduced generalized strongly monomial group, that if chi is a generalized strongly monomial character of G, then this simple component is isomorphic to this repeated cross product algebra. But one has to understand this repeated cross product algebra. So there are lots of actions, a lot of twisting. So I first had this cyclotomic extension of Q, took that cyclotomic algebra, and then matrices over that cyclotomic algebra, again cross product over that, and so on. So this is theoretically it's okay, but then does it really help you to find, for example, if I want to find the Schur index of this algebra, is it really helpful? Of course, to do that, one needs further work, which is, so these two works, which I have just said, that generalized strongly monomial groups and the simple component, the structure of this simple component, this appeared in this paper. And then in this paper, we proved that the class of generalized strongly monomial groups is very, very large. We connected monomiality questions with the generalized strongly monomial groups and the structure of rational group algebras. Now I am coming to the latest development, that again, my problem is the same. My problem is to understand this algebra. And from this algebra, we came to this repeated cross product algebra. And this is my now next objective. I'm calling this as A. And I want to understand this algebra. So this is the next work. This is an ongoing work, which is still under preparation with Jyoti. In this, we have proved the following. Now, we like this theorem very much, that if chi is a generalized strongly monomial character of G, then this simple component, which is this, was isomorphic to the algebra A, which I denoted, and which is isomorphic to this cyclotomic algebra. Very, very neat form. E is precisely known. It's the Q zeta, where zeta is the index of K in H, that much root of unity. F is the center of this algebra. K is also known, K0, K1, Kn minus 1, sigma and tau also very explicitly given. So it's a computational proof of Brauer-Witt theorem for generalized strongly monomial characters. And of course, we understand that it's a vast class. And not only that, we are saying that SCHI is Brauer equivalent to a cyclotomic algebra. We are proving that SCHI, the simple component, is isomorphic to a matrix algebra over a cyclotomic algebra, which is stronger than saying Brauer equivalence. Now, what is all contained in this work? I'll just give you the outlines. The first step which we saw was that this algebra A, you remember this repeated cross product algebra, which I told you, lots of cross products and so on. That algebra has a central subalgebra B with the same center. Both A and B have the same center. We produced this algebra B so that this A is isomorphic to K cross K matrices. I am lost. Where is it? Yeah. This algebra A, this repeated cross product algebra, is K cross K matrices over the centralizer of B in A. Okay, what is the advantage of this is the following, that this centralizer of B in A, we proved that it contains Q lambda as a maximal subfield, and such that its dimension over its center is the square of this dimension. And this is what we wanted for a cross product algebra. So because of this fact that the centralizer of B in A, we could prove contains a maximal subfield, which is isomorphic to Q lambda, we could prove that the centralizer of B in A becomes a cross product algebra of q lambda. Q lambda is just to q, you're adjoining the character values of lambda, which means q zeta, where zeta is the index of k in edge root of unity. So because we could prove that this is a maximal subfield of this became a cyclotomic algebra over q lambda. Yes, it becomes, but now the question is, what is this? What is this? What is this? And that also we could give very, very explicitly. We could prove that the Galois group of q lambda over q xi is successive extensions of, you take c naught by h naught, extended by c1 by h1. Ci's by hi's are known from the inductive chain. Extended by c2 by h2, it is of this type. Extended meaning that a group is h by k if it has a normal subgroup h and the quotient is isomorphic to k. So this Galois group is of this kind. It's like repeatedly up to cn minus 1 by hn minus 1. You take c naught by h naught, extended by c1 by h1, again extended by c2 by h2. This Galois group is of this kind, and we could tell what is the sigma. In fact, we could find basis units. We could tell a method to find basis units of q lambda with respect to this Galois group, and which gives precise sigma and this precise tau. This is, technical calculations. So I'm avoiding all those calculations, but just mentioning what we could obtain. So let me tell you, if you apply it on certain group, what happens? What is the kind of structure we are able to see after some calculations? We took this group, take extra special P group. It's a CP cross CP semi-direct with CP. This is the presentation. This group has 3 generators, X, Y, Z. CP cross CP semi-direct with CP. X is in the center. X commutes with Y, X commutes with Z, and YZ is ZYX. This is an extra special P group of order PQ. Now, 2 to the n minus 1 is the highest power of 2 dividing P minus 1. We have taken P to be 1 mod 4 because if it is 3 mod 4, then the structure is easier to give. It becomes a strongly monomial group. So we took P to be such that it becomes a generalized strongly monomial, so that it's a better class, wider class. And now you look at this automorphism theta of P given by this. R is the primitive root mod P, and R to the T is K and Q are integers with this property. And so the idea is to take an automorphism of P of order 1 more than the highest power of 2 dividing P minus 1. This theta is an automorphism of order 2 raised to the n, 1 more than the highest power of 2 dividing P. Now you again take the semi-direct product, take P. Theta is an automorphism of P of order 2 to the n. So you take its semi-direct product with the cyclic group of order 2 to the n. And what you do is construct this group. It's a group with 4 generators, X, Y, Z, W. W is of order 2 to the n. And this is, we took this group. And what we saw that this is a generalized strongly monomial group. How we proved that this is a generalized strongly monomial group? We looked at all the characters of this group. We saw that they were monomial. These are the linear characters, which, because the commutator is P, one can prove. These are all the linear characters. What we could prove was that the non-linear characters, either they are induced from P, or they are induced from linear characters of this subgroup. So it is clear that this is a monomial group because all irreducible characters are monomial. We could prove that these are all irreducible characters. And now from this, we also have Shoda pairs, and also we could sort out the inequivalent Shoda pairs. And what we could prove was that these are inequivalent Shoda pairs, which you obtain from those irreducible characters. And these are all, we proved that these are all generalized strongly monomial characters. And therefore, this is a generalized strongly monomial. And now we try to apply our theorem of the simple component, which we have recently seen. And what we obtain is the following. This is Shoda pair and this is simple component. See, this Shoda pair is just a Shoda pair corresponding to a linear character. So it is an old result of Perles-Walker that this is isomorphic to. This gives you this simple component. There's nothing new which we have done here. Again, this Shoda pair is a strongly monomial, a strong Shoda pair. And then from the work of Oliveira, Del Rio, and Simon, it turns out that the Shoda pair is, the simple component is isomorphic to this matrix algebra over this F. F is this. This is new. These two Shoda pairs are generalized strong Shoda pairs. And what we could prove with our theorem that the simple components are isomorphic to matrices of size p raised to p into 2 to the n over quaternion algebra over F. And this is again quaternion algebra over F. I think this is n plus 1 if I am not mistaken. All right. And this is something new. And if you go back to the Oliveira's approach of Brauer-Witt theorem, that you find strongly monomial, given a monomial character, you start finding strongly monomial characters lying below it, then only GAP can do it. There is no theoretical method to find those, and GAP has its limitations. So this general work cannot be handled, obviously, with GAP. And what we could prove was that if G is this group, which I have described, then its Wedderburn decomposition is of this kind. These are direct sums of these fields, then matrices over this field F, then quaternion algebra, matrices over the quaternion algebra over F. F is this field, and HF is the quaternion algebra over F. And this to our I mean, we are quite satisfied with this presentation of the Wedderburn decomposition, that we are precisely able to tell not only the Schur index of the simple component, but precisely the size of the matrix algebra and everything just from the subgroup structure of the group. Okay, thank you. Happy birthday, Professor Kulkarni. Thank you.
Thank you, Gurmeet.
Thank you, sir.
We can have a few questions.
Yeah.
What did the GAP program do for computing the Shoda pairs?
Yeah.
The
I
GAP programs have been developed.
I cannot hear you clearly, Professor Kulkarni. I can't hear you clearly.
I'll relay his question. He's asking how much the GAP program do. Yeah.
How much GAP can handle? GAP can handle groups up to order 2000, but beyond that, it has its limitations. It depends upon the structure of the group. If it understands the presentation, then if it is within the computational limit, it will tell you, but up to the order 2000, it works very well. It works
No matter
beyond
what
that.
the group is.
Pardon?
Only the order is the limitation.
Order is the limitation, and then beyond the order 2000, the structure of the group has a limitation.
Okay. Any other question?
The order 2000 is not too large.
2000 is not large, yeah, but if you want to see a general class of groups, like for this group, what I said, p cube into 2 to the n, you give any prime p and the answer is with us, but GAP will not tell us this. I mean, we tried to put p is equal to 3, 5, and 7, it doesn't, gap does not go beyond 7. P is equal to 7.
His question is about the efficiency of Sage.
Efficiency of Sage.
Sage program.
Sage program. I've not worked with Sage. I can tell you. But I don't think in Sage you have a function to compute simple components and so on. That is there in gap. Not there in Sage.
Okay, any other questions for Gurmeet? Okay, in that case, let us thank Gurmeet for a nice talk.